Speaking of making things difficult, let's now take this to 2D. Let's do real quick what you need to know about 2D momentum. Oh, I'll never get there, though. Let's see. We've come to a standstill. Do I need to bring in medics? You guys look like... Let's take some pulses here. Okay, 2D collisions. Last little thing, you have a couple of them on your homework here. We consider it important. And basically, all this is remember, momentum is conserved as a vector. So what that means, if you're doing Cartesian coordinates, is that px initial equals px final for the system, and py initial equals py final for the system, and pz initial equals pz final. It's conserved in all three Cartesian directions. We aren't going to get into rotations and all that. Okay, so they're all conserved. Okay, so now, quick thing to tell you is sometimes a 2D problem just uses, I messed up my sentence, 1D conservation. And that is the one in your homework, like the one due next Friday, or Wednesday, where in this standard, you'll see this in all kinds of book problems. A shell or something flies up in the air, all right, and it lands, and right here, something horrible happens, and half of it gets a kick, and half of it gets another kick. It explodes, right? Like that. And I think in your homework we say it explodes in a way that this one just falls straight down. And therefore what you're thinking about is that the apex of the motion, it only had velocity this way. So all you're doing with the explosion is canceling the velocity that way and increasing the velocity of that piece. So it's really a 1D momentum problem. The thing is moving in 2D. You use this information to work on the kinematics, but it's really a 1D problem. It's a 1D momentum. It's not really 2D momentum.